kinematics, I didn't cover it a ton last time. Well, A, because we were running short on time, but B, because it's really just math. As you've seen in your DL, there are tough physics concepts buried in it and stuff that we need to know. However, these kinematics equations are the quadratic formula, the equation of a line, and well, just a number. So let's do a quick example of a ball that's thrown down with an initial velocity that's both down and to the right. So you see this v naught is down and to the right. And after it's thrown, it's only under the influence of gravity. And so there's clearly an x and a y direction here, and we can examine both individually. So that's something that we pretty much always need to do, break things down into components in order to more clearly see what's going on. So let's first look at the y direction. We're asked the time to reach. I know the answers are as close as we can get to the answers. They're all up here already, but we're going to look at time to reach the ground and the velocity right before hitting the ground. So for the time to reach the ground, what we're asking really in that statement is like a relationship between, of course, the time and then the distance traveled. So like reaching the ground is a measure of how far it fell. Like how hard did it start with? H, we call it, and then getting to the ground, which is at 0. And so the kinematic equation we're going to use is the one that connects time to distance traveled, which is this first one here. YF equals, or Y final equals Y initial plus initial velocity in the y direction times time plus 1/2 AY t squared. So that is just the quadratic equation, ax squared plus bx plus c, where x is t, time. And yeah, so we can plug in everything here to find y final, which is 0, right? How long does it take to reach the ground? We know our y initial is h, the height that it started with, plus this vy naught term, so our initial velocity in the y direction times time. So that factor, assuming the velocity wasn't changing at all, that's just how far do I travel due to that initial velocity. My initial velocity in the y direction is -2 meters per second, and I want to know how far I fell after 3 seconds. Then, of course, that would be -2 times 3. It would give me -6. So that gives me the contribution of my change in distance from the initial velocity. But then it gets a little more complicated because there is a net force in the y direction. We do have an acceleration. So if our F net is just gravity, then our acceleration is, of course, just going to be -g, the acceleration due to gravity. And so my velocity is changing over time. So like I said, if my initial velocity was -2, it would fall 6 meters in 3 seconds, but it's only -2 at the first instant. Every second thereafter, it speeds up more and more going down. So the velocity increases, or I guess really increases negatively, becomes more and more negative. It speeds up falling due to gravity, and that's what this 1/2 AT squared term factors in. So because A is -10 meters per second, we'll get this extra term that adds to the distance fallen in any given amount of time, because again, it was -2, but then immediately after, and all the while until it hits the ground, speeding up and speeding up. And so yeah, this equation here is now just a quadratic equation. You could use the quadratic formula, you could use your calculator, whatever. We probably won't have you do that on the final just because I trust that you all you have the capability to solve the quadratic equation, and it's just not really necessary, but we could easily simplify this. If we eliminated h or eliminated v or something, the equation becomes much more easily solvable without any tricks. It's just rearranging like we normally would. Anyway, we could solve that and get how long it took, solve for t, and get how long it took to hit the ground. If we plot this equation, which we've done up here on the top right, y versus t, we see that it does form a parabola, as we'd expect the quadratic equation to do. This is a little weird because in the way we've plugged in values, it says that our y initial is h and our y final is 0, but it looks like on this graph we're starting at 0 and going negative. So that's kind of arbitrary. It doesn't really matter. Like, you can call whatever you want 0. Maybe we're falling from 0 to -h. It would be the same physical situation, just depends on our definition of 0. But anyway, we get a parabola that is sloping downward, right? Because we want our position to become more and more negative as we fall. And then additionally, the slope is increasing, right? It starts with this slightly negative downward slope. That's the initial v naught that we gave it from the throw, and then the slope becomes more and more negative as we move in time because gravity is making it fall faster and faster. And the way that we can demonstrate or plot out the slope over time is the velocity versus time. So we have the equation written out, but just qualitatively first, we want the slope of the y versus t graph to be slightly negative at first and get more and more negative. And that's exactly what this vy versus t graph does. It starts with a small negative value and becomes more and more negative. So let's see the exact equation of this line, the v versus t graph. And we can see here, like we wanted to solve for the velocity right before hitting the ground. That would be an excuse to use the kinematics equation that relates velocity and time and acceleration. And for that, we have our final velocity is just equal to our initial velocity plus acceleration times time, or y equals mx plus b, right? This is just the equation of a line, and that's why the v versus t is indeed a line. So we plug in here, a is again negative 10, and so the slope is negative 10 meters per second squared, and vy naught, our initial y velocity, is just some negative, slightly negative velocity. So that's why we get this negative y-intercept and a consequent constant negative downward slope for vy over time. And then, if we wanted to solve this equation for velocity right before hitting the ground, we would just need to know our initial velocity. And then we would also need to plug in time here, right? If I wanted to solve this equation and I was given my initial velocity, I would need time, but we just solved for that right above. We found the time to reach the ground, and then we can plug that in. So a little bit of work required for that. And then the final graph, we can make acceleration versus time. The easy way to see it is just, well, acceleration is negative 10, and that's always true because gravity doesn't change, and so we just get negative 10 until the ball hits the ground. Another way to see it is the slope of the velocity versus time graph is negative 10, we would find, but it's downward and negative, and so a versus t should be negative and constant, just like the slope is above. This last equation here is not relevant in this case. Well, I guess it is relevant. We could use it for the velocity right before hitting the ground. We know acceleration, we know our final and initial height, and we can and we'd be given the initial velocity. This equation, if you notice, lacks the time component, so this is just sometimes easy to use. The way we derive it is using kinetic energy. It's not really important how we get it, but you'll have it to use, I think, but it probably won't come up. Anyway, it is a true relationship, and it can come in handy if you don't know the time component and you don't want to do extra work to solve it. But this is just kind of an extra relation to have in there in case it comes in handy. But it's not new physics. Yeah. Well, inside trick, it's probably going to be problem 6, the last one. But I would say you'll run into, you could start another way. So I guess you'll know it's not Bernoulli. You'll know it's not a circuit, right? And maybe nothing's spinning, so you know not to use that. But let's say I started to approach this problem from a momentum perspective. In that case, I would say probably that my net force, I would still find my net force due to gravity, and then momentum-wise, I would say, okay, now what's my delta t in order to find my change in momentum? And to do that, I would need to, there's no way to get a delta t, except I could relate I know my velocity over time. What I'm trying to say is I guess you quickly hit a wall where you have no choice but to relate position, time, and acceleration, which maybe that's another way, that's another thing that you might look out for is finding position and acceleration at or velocity at specific times. Relating those things is something that only the kinematics equations provide us. Also, if there's a graph, something like that. Yeah. Okay. Also, a quick tip. I read something, a research paper that said that it can be very beneficial, especially in your studying, it takes 2 seconds. Just try to identify the topics that you're about to use on a problem before you go into it. Even if it seems obvious and you know what equations you're going to use, that kind of self-explanation is really what it is, and it's a much broader category. But just trying to like just zoom out a little bit and decide what this problem is doing, or like what section of the course is talking about, can be beneficial. So anyway, now let's look at the x direction. So in the x direction, the net force is 0, right? We have gravity pulling down and nothing else. So whatever initial velocity we have is what we are going to have the whole time. So I might start here. Well, we could start with the acceleration versus time graph, which is just 0 at all times. And that's probably the more natural way to do it. In the previous graph, I just did things the opposite way so we could see what it looks like to like look at the slope and make another graph. But now going the opposite way, acceleration up to position. Acceleration is 0, meaning the slope of our velocity versus time is 0. Right? So that gives us enough to say that velocity versus time is flat. But in order to know what that actually velocity is, that's just something that we have to be given. There's nothing else in this acceleration graph that tells us how fast the object is moving to start with. And so we can just, I don't know, use cosine, sine, whatever, to find the x component of this velocity. And that's what it will be until it hits the ground, because there's no other force in the x direction. And then finally, the velocity versus time, being a constant positive value, tells us that the slope of the position versus time has to be a constant positive value, which, as we can see, it is. We have a constant positive upward slope in the x versus t graph. And the y-intercept, the slope is exactly equal to the value of the velocity, and the y-intercept we've just chosen to be 0, meaning that at time equals 0, it's at x equals 0, which is kind of an arbitrary choice. We could still do these the same way as we did on the previous slide using the full kinematics equations, except we'll just find they simplify really quickly. The first position kinematics equation, acceleration is 0, and so we're just left with x final equals x initial plus vx times t, and this is the equation of a line, y equals mx plus b, and that's why our x versus t is a line. And then our velocity equation, we just get acceleration 0, and so, as we expected, our initial velocity is the same as our final velocity at all times until it hits the ground. And yeah, so this problem is a lot simpler in the x direction. And if we really wanted to, we can combine them to get the overall position velocity and acceleration. Yeah. Yeah, so it comes from like integrating it, but I guess one way to think of it is, so acceleration, the units, meters per second squared, is like meters per second per second. So like for gravity, every second, the velocity gets increased by negative 10 meters per second. However, when you do that, like when you start at 0, like after, so if we just like plug it in, if we start at rest and just drop something, how far, or how fast, yeah, let's say how far will I fall after 1 second? I would get not negative 10 times 1 squared, which is 1. I won't be at negative 10 meters yet. I'll be at 1/2 that. I'll be at negative 5. The reason being is that it takes me all the way until 1 second to actually reach negative 10 meters per second. From 0 until then, I'm just slowly getting there. So from like 1 to 1/2 second, my average velocity is going to be whatever, like smaller than 10. And so we would only actually travel negative 10 meters if my velocity was negative 10 meters per second the whole time. But it wasn't. It was between 0 and negative 10. And yeah, so that's what calculus like does for us. It like factors in that change over time, the integrating. Good question. Okay, so that, yeah, one more quick kinematics example. Now we just have a block sitting on the ground that's being pushed to the left. So the net force is to the left. We'll say initial position is x equals 0, at time equals 0, and positive x is to the right, so negative x is to the left. The easy thing to do first is just acceleration, right? So if our net force is negative to the left, then our acceleration is going to be negative to the left and constant if the force is constant. So our acceleration versus time is just a constant negative value, which tells us that the slope of the velocity graph is a constant negative value. However, we don't know what the y-intercept is. So you can see in this middle row here, there's 3 different options for the velocity versus time graph. All of them have the same downward, so negative slope. but they just start at different spots. The first one starts at x equals 0 and then starts moving to the left. Its velocity becomes negative. So that would just be something that's at rest and gets pushed and starts moving to the left. The second one is something that initially has a positive velocity, and then that decreases. And what happens here, we have an initial positive velocity, meaning to the right, and what that means is the force slows it down, brings it to a stop where it crosses the x-axis, and then reverses it, and it gets a negative increasing velocity. That would be the second one. And then the third one is just when it's already moving left, and the force just speeds it up and makes it go faster and faster in the negative x direction. And so to distinguish between these, we need to know more information. We need to know the initial velocity of the object at time equals 0. And then from these, they all produce a different x versus time graph as well. For the first one, initially at rest, assuming it starts at x equals 0, which we're told, that would mean that we just start moving in the negative x direction, and our x component gets bigger and bigger in the negative direction, and not only bigger and bigger, but faster and faster, right? Because now the velocity or the slope of this is getting steeper. If it's initially moving right, however, we see the velocity versus time graph is initially positive, meaning we need to start with a positive slope. Here we started with a slope of 0 and got more negative. Here we start with positive and get less positive until we go through 0, where that's the tip of the parabola, where the slope is 0, and the velocity crosses the x-axis, and then it becomes more and more negative, and will eventually cross through where it originally started and keep going in the negative x direction faster and faster. If it's initially moving left, we start with the negative velocity, so we start with a downward sloping velocity at x equals 0 and just get more and more negative. And we actually can see that, or maybe can find, that these three parabolas are really just like sections of the same one. We're shifting it around and moving it up and down, depending on our other components. So, I don't know, that's kind of interesting, but the moral of the story here, other than to reinforce the relationship between acceleration is the slope of velocity, velocity is the slope of position, is that the initial conditions are important in order for making the graph. And so if we were given these numbers, like let's say we were told that our initial velocity is whatever, negative 3 meters per second, then we'd pick this one on the right. If we were told it's positive 3, be the one in the middle. And it's important to be able to distinguish between them. Okay, any questions on kinematics? So this was most of what you'll need to do. Kinematics on the final will probably involve graphing a lot, and so the level of complexity to go up from here is just there's multiple time sections. So you'll see a lot on the practice problems that, it's like from 0 to 3 seconds there's this, from 3 to 5 there's this, so on, and you'll just be given chunks of information, and your job is usually to piece them together into cohesive graphs of A, V, and maybe X, and also maybe find some values. So maybe it would be like if it was this middle column, like at what time does the velocity equal 0? When does the object turn around? Or something like that. You'll never see something where the acceleration is not constant, or at least piecewise. So acceleration will just look like, flat lines moving like this, stairs. You'll never have a changing acceleration, and you don't need to worry about connecting them smoothly or whatever. We can just approximate that it changes pretty instantly, even though it's not quite correct. Okay, now let's jump back to slide 1 and start off at the beginning of the quarter. So for Bernoulli's, remember, unlike 7a when we were talking about total energy, now we're switching over to talking about energy density, so just energy per unit volume. The reason being we simply don't care about the size of a system. We just care about its behavior, which is much more well described by the density. How much fluid is moving through each volume per second. We don't care about how much fluid there is total. So within a fluid system, current is conserved, current being the flow of volume per second. And the way we calculate current is by multiplying the cross-sectional area times the speed, right? So the faster it's moving or the larger the pipe, the more fluid per second can move through the pipe. And current is conserved through every part. So if we I1 equals I2 equals I3 equals I4, so on, within a single steady state fluid system. So as long as they're connected in a single steady-state fluid system, the current is the same. The area and velocity can certainly change, or speed can change, and if one increases, the other has to decrease, and so on and so forth, as we'll see. But their product, the current, the flow rate, has to stay the same. It does not have to stay the same between different systems, though. Like if I have two disconnected systems that are doing two different things in a question, there's nothing that says their flow rate has to be the same, unless, of course, you're told that. Additionally, if I take a system and then I change something about it, I add a resistance, or maybe I narrow part of the pipe, something like that, that can change the flow rate, because when I made a change to the system, it's a new system. But within a single steady-state fluid system that I'm not doing anything to, the current is conserved within all points spatially. Okay. Let's talk about the different types of energy density that the fluid can have, right? Because as it flows around the circuit, we want to know what's happening to the energy that the fluid has. And since we're talking about density here, instead of potential energy being mgh, we use potential energy density where it's ρgh, where ρ is just our mass density instead of the total mass. And so this just tells us how much energy each unit volume of the fluid has. So for potential energy, it's the higher up it is, the higher the potential energy we have. So as h goes up, potential energy density goes up. And this allows us to use standpipes as a pressure gauge. So in this case, there's two different fluid systems. There's the fluid that's in the standpipe that's still motionless, has a current of 0. And then there's fluid going along the bottom that has a flow rate of whatever, I, going from left to right. And they do meet at this point, P1. And so they're two separate fluid systems. They have two different flow rates, but they do share a pressure at the point where they're in contact. Otherwise, that point wouldn't be stationary. So we can use the standpipe to find the pressure at point 1 and then say that that's the pressure in the pipe below it. And to do that, our Bernoulli equation for the standpipe is very simple. We just have delta P plus delta P over volume equals 0. Remember, the deltas are between a final and an initial, right? So here I have my final being PATM and my initial being P1. So that would be this Bernoulli equation that I've written is going from P1 up to PATM, which it doesn't matter which way you do as long as you're consistent. So since my final was the top and my initial was the bottom, I need to do the same thing for the delta H, where my final is the top H and my initial is the bottom 0. If I flipped both of these, I would get the same answer. And so I can solve to find that P1 is just PATM plus ρgh. So it's greater than atmospheric pressure, which makes sense because we're starting at atmospheric pressure and diving underwater. So the pressure should increase. And if P1 is equal to PATM plus ρgh, that also tells us that the pressure in the pipe below it at that point is equal to that as well. So the standpipe being here is a gauge of the pressure in the pipe below. And the higher the water rises in the standpipe, the greater the pressure. And we can see that here. The larger H, the larger P1 is going to be. Okay. Kinetic energy density is, well, we know kinetic energy has to do with the speed of the fluid flow. So the only change we're going to make is, again, switch m for ρ from our typical kinetic energy expression. And then the thing that changes the speed, we can't really observe speed. It's hard to see how fast fluid is flowing. But since we know current is conserved, a change in area is an analog for the change in speed. It will tell us about the change in speed. So if the area goes up, in order to conserve current, speed has to go down. And if the area goes down, the speed has to go up. So when a pipe gets wider, we know kinetic energy goes down. And when a pipe gets narrower, we know kinetic energy goes up. We also have thermal energy density, which we don't put on the left-hand side of the equation. We don't think of this like the other kinds because it can't be converted back. So potential energy density, we can go up and back down. For kinetic, we can go wide and narrow again. But once we turn energy density into thermal energy density, into heat, we're not going to turn it back into pressure. We can't really do that. And so instead, it's best to think of it as just like energy being dissipated. So energy is conserved. That's what Bernoulli's equation is showing us, that all the energy density systems just convert into one another, and total energy stays the same. But in some cases, we can dissipate it into heat, which is why this minus IR term comes in on the other side, all of the changes in energy density now, instead of adding to 0, add to however much we dissipated, minus IR. And so we can see in a pipe with resistance, we have some pressure for the first one, and then we go along the pipe, dissipate energy as resistance, and so the energy density has gone down. Potential and kinetic haven't changed, and so the pressure must decrease, the total energy must decrease, and so we see that the pressure goes down. The standpipe shows a lower level. We have dissipation, resistance, to remove energy from the system, but we can also introduce energy density to the system with a pump. So a pump adds energy density. So instead of minus IR, we have a plus E pump, or I guess in addition to minus IR. So before the pump, we have some pressure P in. The pump increases it, and so P out is larger than P in. It's very important to note that pumps do not change the velocity of the fluid, or the speed of the fluid going from one side to the other. So the speed of the fluid, V in, is the same as the speed of the fluid on the other side, V out, even though the pressure, the energy density, so I would just think of it as like the fluid coming out of the pump has more energy to spend, even though it's moving at the same speed. However, you can change this, like let's say I just have a system, a pipe with fluid flowing through it, and I add a pump. That's a new system, so now the speed can be different. The speed is still the same before and after the pump, but the speed in the system with the pump can be different than the speed in the system without the pump, because those are two different systems. Okay, so putting it all together, we have our complete Bernoulli's equation. On the left side, we have these values with deltas. We have to pick a final and an initial, and sometimes that's not so straightforward. That can be part of the challenge of the problem, is finding the right final and initial. Usually, you just want to connect something that you know to something that you want to know, right? That's, if you look through your problems, that's a general like kind of structure. In fact, I mean, that's how we can solve an equation, by using the information that we're given to extrapolate onto new information. But anyway, these only matter at the initial and final point. So it only matters the height at the initial and the height at the final for potential energy. Doesn't matter what happens in between. Same for kinetic. It only matters what the initial cross-sectional area is and what the final is. Whatever happens in between, narrowing and widening, does not matter. On the right-hand side, it's just the opposite. It only matters what happens in between the start and the end points, right? So if I have resistance in between the two, that is important and plugs in. However, if I have a resistance right before my initial, it doesn't matter. If I have a pump right after my final, it doesn't matter. Only what happens in between my start and end points. And again, what this equation is just an expression of conservation of energy. It's what is my energy doing? I have a total amount. Is it turning into pressure, potential kinetic, or being dissipated as thermal energy minus IR, or being added from a pump? It's really accounting spatially through the circuit. Okay, yeah. I think so, yeah. There's other things like turbulence and stuff that I think you can describe with kind of as like a dissipation term. But yeah, as far as I know, that's pretty much it. I'm sure there's other, like, once you think about like charges and stuff like that, maybe that's something in there. But yeah, this works really, really well for real systems. Delta KE will only change if the area changes. So and that's within a single steady state fluid system. So if we're just looking between point 1 and point 2, the only thing that will change the speed is the area changing. If you change the system, like you add something new, then you have to solve, like then all bets are off. Then you have to like reevaluate. But in that new steady state system, the same thing is true. That within the system between point A and point B, you'll only have a difference if the area changes between those two. Pressure is like, again, pressure is the balancer. So that's usually the last thing that we solve. It will change however it needs to in order to make Bernoulli's equation work, given whatever potential and kinetic energy and other things happen. Okay, so now let's move on to circuits. With fluid circuits, you're only going to see steady state. So no exponentials, anything like that, and you won't see general linear transport with like the delta phi that we talked about for a little bit. fluids is all your steady state. And for circuits, you could see a little steady state, but also this is the only place where exponentials are going to come in. So I'm going to do a general circuit overview with just resistors and batteries, and then we'll talk about capacitors and exponentials, which is the place that you will see exponentials on the exam, and only there. So in a circuit, very similar to fluid circuits in that we have batteries and resistances, and these are just like pumps and pipes with resistance. And our loop rule, or I guess this isn't really our loop rule, this is just like our Kirchhoff's law or whatever, but this is expressing that delta V, the change in energy density throughout a circuit, so instead of energy per volume, we're now talking about energy per charge. I guess I can go on to the voltage piece, where charge is now flowing around. So instead of our fluid, our current, our flow rate being volume per time, now we have charge per time, or coulombs per time, which gives us amps. Pretty much anywhere where you had volume of fluid before, now we just have charge. And just think of it, that's the thing that's flowing around. Is it a little water molecule going around with energy density, or is it a charge flowing around with energy density? Very similar. But it's an accounting of change in voltage as we travel through a circuit, and the way we change energy density of a charge, it's a little bit easier. We don't have to worry about how high it is or how wide the wire is, anything like that. We just have to worry about batteries and resistors. And so any change in voltage energy density between 2 points that a charge experiences will just be due to a battery increasing its voltage or a resistor decreasing its voltage. And we often do this as a loop. So if we start at one point and go all the way around the circuit back to where we started, delta V has to be 0 because we're just subtracting the voltage at one point from itself. We can't have two answers for voltage at one point. And so the loop rule is just a specific version of this where delta V is 0, we're going from one point all the way around, and so we just have to sum up all the voltage changes from batteries and resistors, and we get no net change. So yeah, voltage is joules per coulomb. The delta here is, again, just a change in voltage between 2 points in space in the circuit. The elements here, we have batteries, where the voltage change across that is epsilon. That's just the voltage of a battery, so 5-volt battery, 10-volt battery, whatever. And resistors have a voltage change of minus IR. So resistors dissipate energy density, batteries add it. And batteries will also determine the direction of flow. So remember, we know electrons are the thing that actually flow around a circuit, but we model electric circuits as positive charge flowing around. And so the positive terminal of the battery, the one with the longer side, is where the current flows out of, and it flows around the circuit into the negative side. And then when charge gets pumped across from negative to positive in the battery, we're going up in voltage. So that's going from negative to positive is how it increases the voltage. And then it goes around the circuit and loses that voltage. And we can see that expressed here in our loop rule. Again, our delta V loop from going all the way around is always going to be 0. And so the only things that show up are plus epsilon from the battery, minus IR from the resistor, and that allows us to solve for what current is going to result from this circuit. So the bigger the battery, the larger epsilon, the more current we're going to get. The larger the resistor, the smaller the current we're going to get. And on the diagram here, you can see there's just implementations of this equation instead of just for a full loop for individual pieces. But delta V from 4 to 1 is just epsilon because we just crossed the battery. From 1 to 2, there's nothing, so we get 0. From 2 to 3, we get minus IR. And if we add all these together, that's the same as just doing the total loop rule. But both of these methods, looking at sections of a circuit or the loop rule, may be helpful depending on what we're doing. But they're really the same idea. Not always do we just have a battery and a resistor, though. Sometimes we have a few resistors. And there's two ways those resistors can be arranged, either in series or in parallel. So for series, that's when resistors, 2 or more, are just placed one after another. The current has no choice but to go through all of them. And so we find that the current is the same through all of them. Since I total all has to go through R1, whatever goes through R1 also has to go through R2. So I total, I1, I2 are all the same thing. And that, combined with the loop rule, allows us to find that we can replace these two resistors with an equivalent resistance that's just equal to their sum, R1 plus R2. So if I were to take out R1 and R2 and replace them with a single resistor that feels the same to the battery, in other words, produces the same total current, that resistance would just be the sum of the two. And again, for series resistors, current is shared, but voltage drop is not necessarily, right? Because the voltage drop across the resistor is minus IR. They both have the same I, but nothing says they have to have the same R, right? So if they have different resistances, they will have different voltage drops, and the only thing that must be true is that those voltage drops must sum to be equal and opposite to epsilon, so that we satisfy the loop rule. A little trickier way to combine resistors is in parallel. So in these cases, current, instead of all going through both of them, can go through one or the other. Current can skip R2 by going through R1. Current can skip R1 by going through R2. And so instead of getting all the current going through everywhere, we get it splitting up into I2 and I1. And instead of those being equal, it's their sum that has to equal the total current, right? All of the current that flows through hits this junction. Some of it goes one way, some of it goes the other, but we can't make new current out of nowhere. And then it comes back together and turns back into I total at the second junction. Using that in combined with our loop rule as well, we can solve to find that if we wanted to replace these with an equivalent resistance, we use this equation, where 1 over Req is the sum of their inverses. And so the way that would work is if we remove R1 and R2, so take them out, and just replace them with a single resistor, so starting at the first junction and ending at the second, just replace them with a single branch. Replacing it with that resistor that has the value Req will give us the same total current, or feel the same to the battery as those two that are hooked up in parallel. And we find, based on this equation, that Req is always smaller than the smallest resistor in parallel. They're smaller than all of them. The reason being, when you combine things in parallel, the charge now has more options, right? And so it just becomes easier. The currents are not always equal. In fact, they'll only equal if the resistors are the same. The reason being that more charge wants to go to the easier path. So if R1 is smaller, more charge is going to go through R1. The current I1 is going to be larger than I2, but they'll still always sum up to I total. The voltage drops, on the other hand, are always equal. The reason being, we have one junction and another. No matter which way I get from A to B, I have to get the same voltage drop because I'm just going between two of the same points. So whether I go through R1 or whether I go through R2, I need to have the same delta V. And that's also true of the Req, which this is something that often gets missed. If I replaced R1 and R2 with a single Req, the voltage drop across that Req minus I total times Req would be the same as delta V1 and delta V2. So that's very important. Final thing I want to mention about circuits before I do a little example is power dissipation. There's not too much with this. Power dissipation is just like the energy per time in a circuit. Batteries introduce energy per time, and resistors and light bulbs absorb it or dissipate it and turn it into heat and light. And then also, like, energy is conserved, right? So any energy that gets dumped in by a battery gets dissipated by all of the elements in the circuit. So if a battery introduces 200 watts to a circuit, the total dissipation throughout all of the light bulbs and resistors is going to be 200 watts. Because if watts are joules per second, and so if I pump 200 joules per second in, the most I can take out is 200 joules, and I have to take out 200 joules. Otherwise, I'll get this buildup of energy, which doesn't make sense. Okay, so the way we calculate it for a battery is just current times the voltage. Pretty simple. For a resistor, there's these three different expressions. They really are just current times the voltage drop across the resistor, but of course we can find that in terms of the resistance as well. And all three of these are equivalent. They'll give you the same answer, just use whichever one is easiest. If you already know two of the quantities, then that's the expression you should use, but for some reason, if you only wanted to use one of them, you can always find the third quantity from the other two with one simple step. But yeah, these are all equivalent. So now let's just do a quick example before we move on to capacitors and exponential change. I did this circuit in lecture, so I'll just speed through it. we have a big circuit here, multiple things in parallel and series. How do I know where to start? Well, I can't, like things in series by definition share a current, and the only things that share a current are 2 and 3. Well, I guess 1 and 5 technically do share a current. We could start there, but it's harder to see. 2 and 3 are in series, and I can just combine those. I can't combine 4 and 5 because they don't share a current. 5 gets the current from R4 plus the current from 2, 3, right? In other words, we can't cross a junction when we're combining things in series. Combining things in parallel, R4 and R3 or R4 and R2, I couldn't start there either because R4 is in parallel with this whole branch and not either one of these resistors in particular. So I'll start by combining 2 and 3 by adding them together, replacing them with their REQ. Then R2, 3, and R4 are in parallel, and so I can replace them with their REQ from finding the 1 over REQ is 1 over R2, 3 plus 1 over R4. And as a check, 3 ohms is indeed smaller than 5 or 7.5, so that makes sense that our REQ is smaller. Replace it in there, and then finally I can just add up these 3 to get my total R equivalent for the circuit. So the same I total would come through the battery in this circuit and that circuit and this one and the original one. It's all going to be the same I total. And as I did in the lecture when I presented this, you can work backwards. Now that I know the I total, I can find the voltage drop across each one of these resistors in the third circuit. And then going back one other level, now I can find, well, I know the voltage drop across R2, 3, and R4 now. So this is that tricky thing I was talking about. REQ, or R2, 3, 4, has the same voltage drop as R2, 3 and R4, right? That's the whole point. And so if I know the voltage drop across R2, 3, that's the same voltage drop across R2, 3, 4. I can find the current in R2, 3, and R4 because I know each of their resistances. I can go a step further, split it up even more. But generally, this is how we will simplify, we'll work with circuits like this, where we simplify them as much as we can, find the total current, and then start working backwards to find voltages and currents in specific sections that we're asked about. Okay, so before I pivot into capacitors, I'll just go to general exponential change or exponential decay. Exponential decay here is referring to the fact that it's e to the negative t over tau. It doesn't mean that the actual graph, like the value that we're plotting, has to decrease. As we've seen, and we'll see in a sec, it can increase too. It's just the exponent that's negative. In other words, the rate of change, we'll find, is the thing that's negative, or the slope. The slope decays away. The rate of change of the slope is really the thing. So anyway, the simple version of exponential decay, we just get y naught times e to the negative t over tau, where y naught is the y-intercept, our initial value, and tau is the time constant. It gives us some time scale for the decay. So if we plug in t equals 0, as desired, we get y naught. That's our starting point. If we plug in t equals tau, the time constant, we get y naught over e, or e to the negative y naught times e to the negative 1. And so we get this decay away to roughly a third of y. And that tells us this time scale for a decay after a few time constants will be pretty much at equilibrium. And then if we plug in a time that's much greater than tau, then we'll get 0. So we'll be at equilibrium. Another way so we can split this up. Before tau, we get this relatively steep slope. Things are changing quickly. And then after that, things start to slow down. After another tau, they'll be very slow. So tau does give us this characteristic time scale. If it's seconds, after a bunch of seconds, the circuit will be at equilibrium. If it's hours, we'll need to wait a bunch of hours for the circuit to be at equilibrium. Another thing I want to say about tau is that it is true no matter when you start. So what I mean by that, we start at time equals 0 with a value of y naught. And to get to y naught over e takes a time of tau. That's what the time constant means. However, what if we start at tau and go forward another tau? So I start at time t equals tau with a value of y naught over e, and I go another value of tau in there. Now I plug in time equals 2 tau, right? Because now 2 tau has elapsed from the beginning, and I get y naught times e to the negative 2, or y naught over e squared. In other words, it's this value, y naught over e, over e again. And so no matter what time you start at, it will always take a time tau to get to 1 over e of that original value, or within 1 over e of equilibrium, right? And same thing is true with half-life, where the time it takes to get from the value you're at to halfway toward equilibrium always stays the same. So to get from 10 to 5 takes the same amount of time as to get from 5 to 2.5, as the same amount of time as it takes from 2.5 to 1.25, so on and so forth. The difference between them, half-life and time constant, is they're just, their uses are, their convenience level is different at different points. If we're just writing out the equation, or we have values like capacitance and resistance and stuff, the time constant is easier because A, it shows up right in the equation in this simple form, and we have neat expressions like tau equals RC, like we'll see. However, if we just have a graph, it's not so easy to work with because 1 over e is a pretty ugly number, and that's not something that shows up. But half-life is an easy number, right? If y naught is 10, half-life occurs when y equals 5, and that would be easy to find. So usually, if you are working algebraically, you'll end up using tau, and if you're given a graph, the easiest thing to do is probably to look for the half-life and then just use the simple relationship that t1 half-life equals tau times natural log of 2. It'll be on your equation sheet. But if you have one, it's very easy to find the other. So just do whichever is more convenient based on the information that you are given. Okay, so now let's connect this mathematical framework over to capacitors. So what are capacitors? They're plates. They're conducting plates with sometimes neutral charge to start with. And by connecting them in a circuit, we pump charge from one side to the other and build up an excess of positive charges on one side and of negative charges on the other. And the reason this obeys exponential decay is as we pump more and more charge, they repel each other. And so it becomes more and more difficult to pump charge. And so the amount of the flow rate, the current, slows down until eventually it reaches equilibrium, which is exactly what exponential decay describes, where it evolves quickly at first and then slowly reaches equilibrium. So mathematically, the voltage change across the capacitor comes from the charge divided by the capacitance. So delta VQ is Q over C. The bigger the capacitance, let's say we have two capacitors with the same capacitance. Yeah, that's it. Two capacitors with the same capacitance. If I put more charge on one than the other, that one will have a larger voltage change across it because it will be harder to push all that charge onto that capacitor. The more charge, the harder it is to push, so the larger voltage drop. However, now let's take two capacitors, one with a much larger capacitance, and put the same amount of charge on both of them. It will be much easier to put the charge on the bigger capacitor because there's more space for the charges to move out, and so we'll get a smaller voltage drop. So that's why Q is in the numerator here, C is in the denominator. Larger charge means larger voltage difference. Larger capacitance means smaller voltage difference, or it's easier to put the charge on that capacitor. So now incorporating into a circuit, what we're really just doing is taking the plates, adding a resistor, but taking the plates and just bending them toward each other. It doesn't affect the way a capacitor works other than it actually makes it a little, increases the capacitance a little bit because the positive and negative charges can attract each other, which makes it a little easier. But that's not something you'll have to take into account. The important part here is that now we can see how these function in a circuit, which now, even though the charges don't jump across from one plate to another, there can still be current in this circuit because the battery is pulling charge from one plate. So I take a positive charge off of the left plate here, leaves a negative in its path, or in its place, and then goes around the circuit and pops on this side. And now we have an excess positive on the right, excess negative on the left. And that repeats until the voltage on the capacitor is as big as the voltage of the battery. In other words, the battery cannot pump any more charge onto the capacitor. The direction can get a little tricky, but when you're charging a capacitor with a battery, the battery is the one that's determining the direction of the current. The battery is the one that's pumping the charge. And so we still have our general current flows out of the positive side of the battery. And so that's how we know that the positives are going to end up on the right and the negatives are going to end up on the left. Okay, so we can still use our loop rule here. And now with all three elements here, we get 0 going all the way around, and we have a plus epsilon from the battery, a minus Q over C from the capacitor. The way we know it's minus is because we're going in the direction of current. So clockwise here, we're going from positive to negative, right? So that's a drop in voltage, and then, of course, minus IR across the resistor. So now let's take a look at this over time. At time t equals 0, if the capacitor starts uncharged, that Q over C term is going to go away, right? So when the capacitor is empty, it provides no feedback. It's easy to push charge around, so we just get our normal epsilon minus IR, and so we can solve for our initial current, and that will be the highest value of current this circuit sees, because immediately after this, some charge will build up, and that causes the voltage change across the capacitor to become non-zero, and if Q over C increases, then I, or IR, but R doesn't change, so I has to go down in order to compensate. So that's the math part, is just saying if this term increases, this term has to decrease to make it still equal 0, and physically what's happening is more charge is building up, and so it's getting harder for the battery to push it, and so the rate at which current is flowing around, the rate at which the charges are going from one side to the other, is decreasing. Until finally, the charge reaches a maximum. Once Q gets so big that Q over C is equal and opposite to epsilon, we know that I has to equal 0. And at that point, the voltage across the capacitor is equal and opposite to that of the battery, and the battery is just simply not strong enough to put any more charge on it. And we've successfully charged the capacitor up to the voltage of the battery. So if I have a 10-volt battery, I can only charge the capacitor to 10 volts, 20 volts, 20 volts, so on and so forth. So I think I just doubled up on these slides for some reason. So now connecting this to the actual exponential decay equation that we have, let's look at charge. So this one's a little funky because it should conceptually follow the exponential decay behavior, where charge is easy to put on at first and it rapidly changes, and then over time it becomes more and more difficult until we reach an equilibrium, and it slowly reaches that. However, charge doesn't decrease, it builds up. So we don't want that downward sloping exponential decay we had before. So we have this different version. It's still exponential decay because, again, the slope is the thing that's decaying away to 0, and that comes from the fact that it's e to the negative t over tau. Otherwise, it would be exponential growth, which maybe you see in population dynamics or something like that, but not here. So anyway, still exponential decay. It's just growing exponential decay. And the new form of it we'll just give you here is Q naught times 1 minus e to the negative t over tau, instead of Q naught times e to the negative t over tau. So at early times, capacitor is empty, and so charge builds up really quickly, but as charge builds up, it becomes harder and harder to pump it on, and so it slows down until it's totally full, and the system's at equilibrium. Charge no longer changes, meaning the current is now 0. And to solve for this value of Q naught, we would look at the final state, because if you look, Q naught, it's not actually the initial charge, but the final. It's the equilibrium charge. To find that, that would be the maximum charge that's built up on the capacitor. We know that occurs when the current is 0, and so in that case, we could just do our loop rule for equilibrium, which is just epsilon minus Q over C equals 0, and that would let us solve for the capacitance, for the charge, based on just the voltage of the battery and the capacitance, which makes sense, right? Because if you want to know how much charge can you build up on a capacitor, you just need to know how much voltage do I have to do it, and what is the capacitance of the capacitor. So there's our exponential decay for charge. Let's say we wanted to look at current. Current also does this thing where it starts at a maximum value and slowly approaches equilibrium, except current decreases. Like I said, it starts at a maximum value. And so it follows this more typical I naught times e to the negative t over tau, where at early times it's large, quickly dropping, and then as we approach equilibrium, it evens out. And to find the initial current, the current here, by definition, it's the initial one, and so we would look at the initial loop rule, when the capacitor is not in play at all. What is the current that I start with before any charge is built up? And that would just be epsilon over R, like we normally find. Okay. Finally, we have discharging a capacitor. So once we charge up a capacitor, we can remove it from the circuit. And it's happy there. Well, not happy, but it can't discharge. It just has a lot of excess charge on one side and a lot of excess opposite charge on the other. And if we connect it across a resistor with no battery, now it can discharge the other way. So now we connect it. The charges have a way off. These positive charges really don't want to be here, and so they flow back around. Now there's nothing fighting them, so they will just continue to do so until it's discharged. And we'll find this also obeys exponential decay because the charge really wants to leave early on because they're packed on there. And as more and more charges leave, they're less and less in a hurry because there's more space on the capacitor. So at time t equals 0, our loop rule is just the maximum Q over C for voltage drop across here. And then that would let us solve for if we want, solve for the current across the resistor. After a little more time, some of the charge has left, and so Q has decreased, I will also decrease, and then at time t equals 0, charge is gone, no current, and we just have a bunch of metal, neutral metal, sitting there. So what this would look like if we plot the voltage over time, on the top we have the voltage of the capacitor. Well, it's really the same graph, but on the positive side, we have the voltage across the capacitor. Now the capacitor voltage is positive because the capacitor is now determining the direction of the current. Instead of the battery pumping it up the way it doesn't want to be pumped, now the positive charge is flowing away and around, and so in the direction of current, we're going minus to positive, which is an increase in voltage. So when the capacitor is discharging, delta VC is positive. And that's why we get this positive voltage decaying away to 0, whereas the resistor starts with this maximum voltage drop across it with the maximum current, which decays away as current fades away to 0. And, as it should be, delta VC and delta VR are always equal and opposite so that they add to 0. And that's just an expression of the loop rule. Because going around the loop, I just crossed through the capacitor and the resistor, and my voltage drop going around a loop, no matter what's happening, steady state or not, needs to be 0, because it's just energy density conservation. Questions about exponentials or circuits? Okay. Moving on to vectors. I'll speed through this because we've been doing this for a long time, but vectors have a magnitude and a direction, so graphically we can just make them an arrow that point with a length. That's the magnitude, and a direction, which is where it's pointing. And then to add them graphically, we can just stack them together and connect the start and the finish. So what this is saying here is that adding up F1, F2, and F3 gives me this Fnet. It does not matter the order. I could do any order of F1, F2, and F3, and I'll get the same resulting Fnet. And then also, with vectors, you're free to cut and paste them wherever you want. You can't rotate them, and you can't stretch them, but you can always just pick them up and move them around to add them tip to tail. So yeah, that's adding vectors graphically. To subtract them, we just make an addition is the easiest way. So F1 minus F2 is the same as F1 plus negative F2. Negative F2 is just F2 facing the other way, and then we can add them the same way that we normally would. So this is all great for graphical addition. It's good to check our work, and it's the foundation for what we're going to do algebraically. But algebraically, each vector has different components. So we still need two quantities to describe a vector, but instead of describing magnitude and direction, instead I can give you equivalently the distance in the x direction and the distance in the y direction, a pair of components. So instead, I can describe F1 instead of magnitude and direction as F1x and F1y. And as we'll see, I can go back and forth between the two with trigonometry. So what this allows us to do, component by component separation, is add them very easily algebraically. So for the net x component, I just add F1x and F2x. Same for y, and so my Fnet is much easier to find. And the x and y components are completely independent. And this will ring true for like the rest of the rest of the lecture, I guess, that for these problems, if I can successfully separate x and y, I can have two much simpler one-dimensional problems and then just combine them at the end if there's part of the answer that asks me for something general. So how do I find the components? Like I said, with trig, I would not memorize that this is sine and this is cosine, right? I would just learn that sine gives me the opposite side, cosine gives me the adjacent. To find the components, it could very easily be swapped if I gave you a different angle. And again, this is true for forces, this is true for angular momentum, anything. Whenever you're doing trig, just know what you're talking about. It might not even be sine and cosine. You might use tangent or something like that. But it's, at the end of the day, it's just a relationship between the sides of a right triangle and the angle. There's just three of them, sine, cosine, and tangent. And it would do you well to practice using them in different situations. To go back and forth, so to go from components back to magnitude and direction, we have Pythagorean theorem and inverse tangent, which we should have had lots of experience with. So also I'll speed through this because we talked about it a lot. We know forces are vectors, units are newtons, and they're pushes and pulls. They change the motion of an object. By motion we mean momentum, which we'll talk about in a sec. But if the net force is 0, the object's momentum does not change. And if the net force is some quantity, then the momentum will change in that direction. It's also important to note that forces are done by one object, or on one object by another, or by one object on another. It doesn't matter, but, and as we'll see later on too, one of the reasons it's so important to write them like this is not just so that we are consistent when we're making our diagrams. Like every force that you draw on an object needs to be a force that's on that object. But also it helps us keep track that every time we have F on A by B, there always is a corresponding minus F on B by A, which we'll talk about in a little bit. So, what is momentum? So the thing that forces change, momentum is just mass times velocity. So it's in the same direction as our velocity and increases with increasing velocity, but an object with more mass will also have more momentum, right? If we toss a bowling ball and a golf ball with the same speed, the bowling ball obviously has more like inertia to it, like it has something more, and that something more is momentum. And so momentum helps us keep track of how things respond to forces, particularly by a change in momentum. Delta P is equal to the net force times some change in time. So the longer we apply a force, the more impulse it transfers toward it, or the more its momentum, the more the momentum of the object it's acting on will change. The direction of F net is the same as the direction of delta P, which makes sense because if I push something to the left, so my net force is to the left, I want its momentum to increase to the left. However, that doesn't tell me anything about its final momentum, or it doesn't tell me the full story about it, right? Because it depends what my initial is. If I was initially moving to the right and a force pushed me to the left, my final momentum might still be to the right. It'll just be smaller. Or maybe I was stopped, in which case a net force to the left would push me to the left. Maybe I was moving forward, in which case a force to the left would make me be moving now forward and to the left. What I'm trying to say is that it's important that F net is in the same direction as delta P, not necessarily P final. An object can still have momentum even without a force, right? It just requires a force to change that momentum. So just because an object's moving, even sometimes a problem will say like a ball is kicked or thrown or something like that, we shouldn't factor in whatever force caused the object to move if it's not part of the interval that we're talking about. So like in that case where I started the lecture today with kinematics, where the ball was thrown down and to the left, we never cared about the force that caused the ball to get to that initial speed, right? Because we're starting our problem, time equals 0, is once the ball is left the hand with the initial velocity under the influence of gravity. So that force is not in the picture. The only forces that change momentum, only look at momentum changes due to forces that are currently acting on it. We can also total the momentum in a whole system to consider it as a whole. For that, we just add up all the momenta. We know they're vectors. We know how to add those. And then we can look at systems together by whether or not an F net acts on the whole thing. So objects within the system might be colliding and interacting, causing forces on another. But if there's no net force on the whole thing, in other words, if there's no force caused by something outside of the system, all the forces are caused by objects within it, then our total change in momentum will be 0. We just have an amount of momentum in this bubble and it doesn't change. On the other hand, if it's an open system, if there's a force caused by something that's not already in the system, then we will have a change in total momentum, and that will exactly be equal to whatever the F net is times delta t. So looking at a simple momentum charts are a great tool. Remember, they just organize equations for us. Going from left to right, we're saying P initial plus delta P equals P final. And going from top to bottom, we're saying that all the momenta in the system at a particular time add up to the total. So for this case, we have a ball that's moving to the right, colliding with another ball that's at rest. And so our initial state, ball 1 has some momentum to the right, ball 2 has 0, and so our total is just whatever the momentum of ball 1 had. If there's no net force, that tells us that our delta P total is 0, and so our our P final is whatever our P initial was. So the total momentum in the system, however it's exchanged between the two balls, is just equal to whatever the initial momentum that ball 1 had. Then we're told something about the final state, and we need a little more information. That could be a statement about its elasticity. It could be a statement about, like this, where the ball 1 stops. But we need some information to know something about what happened in the collision. It's not just enough to know that they collided, because there's a lot of different ways they can do that. But if ball 1 comes to a stop, we know P1 final is going to be 0. And so ball 2 is going to have all of this momentum, right? Because we have the same total momentum in the system. That just tells us that ball 1's whole momentum got transferred to ball 2. And let's say we were asked what the final velocity of ball 2 was. We can now easily solve it because m1 times v initial has to equal m2 times v final. And in this case, if m2 is larger, like it appears to be here, then we know that, of course, the v final is going to be smaller because it has the same momentum but a larger mass. Last thing we can do is look at the delta P column. P1 goes from having this positive momentum to 0, so it must have an equal and opposite momentum change. Ball 2 goes from 0 to having a positive momentum, so it must have a change that is equal and opposite to the momentum change of 1. Or we could just say delta P1 was this, and our total is 0, so that's what delta P2 has to equal. But either way, we find that they have these equal and opposite delta P's, which is what we want because the total needs to be 0. There's no net force, and so any force that occurs here or any momentum transfer has to be equal and opposite. I guess using the language of this unit, this model, the momentum transfers are equal and opposite. But we know, moving on to Newton's third law that we learned more recently, that we can also express this saying that this force is equal and opposite to this force. And the relationship can be proved by just saying that the time that they're in contact, the delta T, the delta T that connects F net and delta P are just related by the time that they're in contact. Okay. So just kind of a restatement of this, our velocity, momentum, and change in momentum. And the last piece of this unit was elasticity and inelasticity, which I already mentioned. The easiest way to deal with these are just calculate the initial kinetic energy total in the system and calculate the final total kinetic energy. If they're equal, elastic. If they're not equal, then it's inelastic. One thing that people often get tricked with is that the speed is the thing that matters. So if you have components of velocity, you need to use the Pythagorean theorem first and calculate the speed, then plug it into kinetic energy. You cannot find like X kinetic energy and Y kinetic energy. That doesn't work. So make sure you have the magnitude. Direction doesn't matter. And you can never go wrong just calculating it and checking, but the one case where you can tell whether it's elastic or inelastic without calculating is if you know they stick together. If they stick together, that means it was perfectly inelastic, meaning it lost the maximum amount of kinetic energy that it could. Otherwise, if they bounce at all, you know that it could be could be elastic or inelastic. You have to do the math to figure it out. There's not too much more to it there. Okay? Now let's transition over to angular momentum and torques. So we saw that these quantities are analog. Like this whole unit is really analogous to the linear momentum in a lot of ways. instead of velocity being a change in distance or a change in position over time, we have angular velocity, omega, being a change in angle over time. Instead of linear momentum being mass times velocity, we have angular momentum, L, being angular or rotational mass or rotational inertia, I, times rotational velocity, omega. And finally, we can change L, our angular momentum, not with a torque, but not with a force, but with a torque, which is clearly dependent on a force, what we'll talk about soon, but applying a torque over a time changes angular momentum. Now, all these things are vectors, but these vectors work, the vectors work the same way as other vectors, but to determine their direction, we need to do a little more work. Instead of just velocity being the direction an object is moving, and that's the direction of the vector, we need to use our right-hand rule. So when things are rotating, or when a torque wants something to rotate, we wrap the fingers of our right hand in the direction of that rotation, centered around the axis of rotation, and our thumb will point in the direction of the angular velocity or angular momentum or torque or whatever we're trying to figure out. We also introduced these two new symbols for into and out of the page. The reason being, if something is rotating in the plane of the page, the right-hand rule will point in or out of the page. And like we saw in the quiz, into and out of the page are not reserved only for torques or for angular velocity, right? Something can be rotating in the plane that we see on this slide here, like in the horizontal plane that goes into and out of the page. So in that case, the direction of the rotation, the angular momentum and the angular velocity, is actually up. So these into and out of the page do not just have to be used for torques, they're just a different direction, and we have to use our right-hand rule to figure out what's going on. So to break down these quantities, just again one more time, angular velocity, change in angle over time. So theta is measured in radians. So if you're not comfortable with it, make sure you can switch your calculator easily between degrees and radians, because you probably will see both. But radians are technically unitless. We often write omega as radians per second, just to remind us that we're talking about rotations. But when we're evaluating other units, we can just say inverse seconds or per second. Angular momentum is when we multiply this angular velocity by our rotational mass. So how do we calculate that rotational mass? Like, we want something that distinguishes, like let's say we just have like a little saucer that's spinning at some angular velocity, and then a carousel that's rotating at the same angular velocity. Clearly the carousel carries a lot more momentum with it, and so we want that to be described somehow. And the way we do that is with our rotational inertia, which is our analog for mass for angular cases. And it is dependent on the mass, but not just the mass, it's the configuration of the mass. So where the mass is in relation to the axis of rotation. So I guess it's also dependent on what the axis of rotation is. I could take the same object, rotate it about a different axis, and it will have a different rotational inertia. And the way we calculated it, this all comes from this expression where I is the sum over mr squared for each of the mass elements, where m is the mass of that element, and r squared is its distance from the axis of rotation squared. And it's the distance from the axis. This also came up on the quiz, where we had a ball swinging around a pole from a diagonal string, and it did not matter, well, I guess you needed the number, but the length of the string is not the thing that we plug in for r. It was the perpendicular distance from the object or the mass element to the axis of rotation, which was the vertical pole axis. So yeah, that's an important little piece. Rotational inertia will only have you calculate, like I said, with discrete, like one mass here, one mass here, one mass there. If it's a solid object, like a sphere or a shell or a plane or something like that, we'll just give you the number. So you should be able to use it and also argue just qualitatively how would doing this change the rotational inertia or something like that. Okay. Torques. So now we know how to describe angular momentum. How do we change it? And it is with a torque. And we found that they are related to forces, but not every force will produce a torque. And the two things we need are the force to be separated from the axis of rotation. So the r vector here points from the axis of rotation to the force, where the force is acting. And the force also needs to be at least somewhat perpendicular to that r vector. So if the force is right on the axis of rotation or parallel to the r vector, then it's not going to produce a torque. So let's say we have a force that is pointing diagonally here. We can see that it does have a distance away, and it is at least partially perpendicular to r. So how do we calculate the torque? Well, we just use F perpendicular times r. And so here, F perpendicular, given this angle theta, F perpendicular is the opposite side to theta, and so we use sine. There's a typo in the bottom right. It shouldn't be cosine, but we use tau is F times r perpendicular. I'll also note here that what I've switched to is extended force diagrams. So instead of drawing forces acting right on a point where an object is, I'm drawing the force where it's acting because the location is very important to determining the torque. We could also have a case where, it's a very similar case, but we have a force. It is a distance away from the pivot point, the axis of rotation, and it's not perpendicular, but some of it is, except in this case, F is already vertical. So why mess it up? R is the one that's diagonal. So instead of finding F perpendicular, we can also just find R perpendicular. And since F is vertical, R perpendicular is the horizontal piece, which in this case we find from cosine. And it doesn't matter which one. Tau is just F perpendicular times R, or F times R perpendicular, whichever is easiest to find. And I recommend just whichever one is already perpendicular or whichever one is already horizontal or vertical, just leave it that way and break the one that's diagonal into components. So this is just summarizing everything about angular momentum. The last thing I had was Newton's laws. We just covered these, but to review, first law is really, and second law are really just the same things we learned from the momentum unit, where net force changes an object's momentum, except now instead of talking about delta P, like a change in momentum, we're talking about acceleration, which gives us our instantaneous change in velocity times mass. So really our instantaneous change in momentum. But these two things are just the equivalent, are just different ways of viewing those things that we learned before. If there's no net force, our velocity doesn't change, or our momentum doesn't change. And our third law, anytime we have a force, there's always going to be an equal and opposite force on the object causing it. We just don't always care about it. For instance, we are very often drawing Fg as the force of gravity pointing down on a bunch of objects, and we almost never draw a corresponding force on the Earth that's pulling back up. That does exist. It just, usually the Earth isn't part of our system, and we don't care about what happens to it. And it's so big, its mass is so big, that the force we exert on it causes no acceleration, and so we ignore it. But this is always true. There always is that corresponding force. All right, that's all I got for today. My next review session, or my other one, is Thursday evening in this room from 4:45 to 7. That I'll do on the Blackboard. Bring questions, practice problems, practice finals, that type of stuff. And it won't be recorded because, it's on the Blackboard. But I will post this.